Okay, thank you. So I will conclude the first lecture giving you a more exotic example of Wick calculus. So the example is coming from discrete probabilities. It's going to be some more exotic example in the in general context of the lectures, but I wanted to show you that there are plenty of ways of doing Wick calculus. Some are less obviously connected to what I'm going to explain later. So the idea is to fix a finite set. Say, for example, the integers from 1 to n, and look as a probability space to all functions from S to, first to all functions from S to minus 1 plus 1. So Bernoulli variables associated to each element of the set. I will write omega for this. For the elements of omega. So the elements of the Bernoulli space. And one point I want to emphasize immediately is that, because I will use it at the end, is that we can interpret these random variables as random paths. So to omega, I would associate a path written that way with a hat, which is defined in the following way. Omega s is going to be the sum for t less than s of omega t square root of delta t. For obvious reasons, because we want to do something approximating random paths like the Brownian motion. So in that case, the situation is particularly simple. So all computations can be done by hand. So the space of square integrable functions on omega is simply the set of functions from omega to c. And I can try to orthonormalize this set of L square functions. I can do it that way. Given a subset of S, I introduce the function kappa t of omega, which is defined by the product over the elements of t of omega of t. Then it's very easy because we have Bernoulli random variables associated to each element of set. It's easy to see that the chi-t form an orthogonal basis, actually an orthonormal of L square of omega. So it's easy to see they are orthogonal. You just have to make the computation and use the fact that you have this plus 1 of -1 values on the elements. And it's easy to see that it's a basis for the dimension reasons, because the set of these functions is of cardinality, the cardinality of the space of functions from omega to c. Sorry, the space of, yes, the space of function, which is 2 to the power s. So this property is elementary. But then you can use it to decompose so square integrable function. And so if you have a random variable x, you can write it as the sum over all subsets of S of a coefficient t of x times chi t. So this is what I would like to call the discrete chaos decomposition. It's also called in the literature the Walsh decomposition. And these are called the Walsh coefficients of X. So we can try, sorry, we can try to do with this kind of random variables and situation the same computations we did in quantum field theory or with Gaussian variables. For example, you can ask, what about products? So is there a good notion of Wick product in that case? It happens that it takes a very nice form. If you think to what is Wick product, if you take the Wick product of two Wick products, so the idea of the Wick product is that you put all annihilation operations to the right and all coefficients operations to the left. So of course, if you look at this product and you compute iteratively the associated Wick product at this level and the associated Wick product at this level, and then you compute the overall Wick product, it's clearly the same thing as doing this. Because globally, you're just moving annihilation operators to the right systematically. So this is telling you that there's a consistency between what I explained and the construction of products. So products should be compatible with Wick constructions. If you think in these terms, in that situation, what you get one gets the following law. So if you want to multiply, have a sort of Wick product of chi t and chi u, then the right definition is to say that this is chi disjoint union of u and t, if the intersection of u and t is empty and 0 else. I think this is a very nice illustration of how these things works, because they boil down to elementary constructions in a discrete case. And you can relate these two processes. So I will make a rescaling. I will rescale the Walsh coefficient by normalization factor 1 to the square root of delta t to the power k, the cardinality of the set t factorial times the initial Walsh coefficient. If I do this, then what we get is that x omega can be rewritten. So we know it arises in terms of the Walsh coefficient in this way. But we can rewrite it as the sum over t. So all the subsets of S, t factorial, so the cardinality of t factorial, times this rescaled Walsh coefficient times omega t1, so delta t omega tk delta t. If you try to understand what this means, these are time increments of the process. The delta t is just some fixed increment, yes. That you have to, I mean, if you want to use this, you have to fine-tune delta t to the length of the time interval you consider and so on. I don't do it, but typically delta t would be something like t, or you can think of delta t as t, a fixed finite time t divided by the cardinality of S, something like this. Okay, so if you think what this term means, this is the discrete analog of an iterated integral. You're just summing over k time increments. And so you have a decomposition of paths in terms of iterated integrals. It happens that one can move from this discrete picture to the continuous picture. And if you do so, I won't explain this. I will maybe do it later. I will postpone because I want to make the second lecture and introduce Hopf algebras and everything. But if you go to the continuous picture, what you get is a discrete analog of the Wiener decomposition of, say, square integrable variables associated to Brownian motion. So I won't explain details. You can find them in this article by several people, including Oxendel, I mentioned at the beginning. But if you go to the continuous case, you get the idea that if you have a path that is constructed typically out of integrations over the Brownian motion, then it has a canonical decompositions in terms of iterated into integrals depending on the Brownian motion. And this is the discrete analog we have constructed. And if you go to these Wiener decompositions, they are very nice because they also involve Hermite polynomials. It's also fundamental results in stochastic integrations, but it fits this overall picture I'm trying to give. Although I won't come back to processes, but there is general consistency and this general claim that Wick constructions are really the common basis of many different constructions, including these Wiener chaos decompositions or expansions associated to Brownian motion that take this particularly simple form in the discrete case. So I will turn now to the second lecture, which is on Wick calculus and Hopf algebras. As there will be several lectures discussing Hopf algebras, I think, I will also introduce the basic definitions. So here there are many references. I just give you the titles. You can find the reference on the web. So I will start discussing the original Wick paper, the evaluation of the collision matrix. (1950). It's a very nice article. I will then explain Hopf algebras. So if you want a general reference on Hopf algebras, we work with Pierre Cartier textbook, already starting from the basics where you can find all the classical results on Hopf algebras. There are also some short discussions about the topics I'm going to address during the lectures. And then I will use papers we worked with Kurush. On renormalization. I will explain how Wick renormalization relates to classical renormalization in quantum field theory. And I will try to show you that it really fits perfectly, in the sense that the construction that gives the Wick polynomials is really algebraically the same that the one that allows to perform renormalization in quantum field theories in general, beyond the case of the very fundamental renormalization, which is the one obtained by Wick products and time-ordered products. And then I will use also an article we wrote with Kurush, Nicolas Tapia, and Lorenzo Zambotti. Which is on the way the construction of Wick polynomials can be interpreted in terms of algebras. And if I have time, I will also discuss a very nice paper which contains a lot of insights on the relations between quantum field theories and of algebras, which is an article by Bruder, Hauser, Abeti, and Höckel from 2004. That is called Quantum Field Theory and of Algebra Cohomology. Well, there are plenty of insights. And it's really correlated in general with the work they did with what I'm going to say. Although they have a slightly different point of view. They really emphasize general techniques of deformations in the theory of algebras, like so the cohomological approach and what they call Laplace pairing that I will introduce in the end. Okay, so this will be these are the references. We start from Wick's article. So what did Wick? I will just explain orally the general ideas in the article to spare time. So he takes an example. He takes the example of a quantum field theory describing an electron-positron field interacting with the quantized electromagnetic field. But the precise form of the theory is not really important. The idea is that he wants to study a generic situation where you have creation and annihilation operators, and you want to get rid of infinities, precisely in the way I explained. So the purpose of the article is really to make sense of this kind of computations in a systematic way. In his terms, what he says is that the main problem to be solved is carrying the ID. So this ID of normalizing the quantum fields at inception in a certain sense of the theory. The main problem to be solved is carrying this ID in one of algebraic technique. That is to introduce a convenient notation to handle the rearrangement process easily. So this rearrangement process where you move annihilation operators to the right. And this is what he does in the article in an axiomatic way. And the main goal of the article is to compare, I use this terminology and notation here. So you want to compare S products, which is what we introduce as, and what is called now usually Wick products. With time-ordered products. And to do so, he has an axiomatic approach. It's It's really mathematical physics. He wants to develop tools for mathematics to understand constructions in physics that at the time were not correctly understood. And his axiom is that the S product is multilinear. So it's a standard product. And it has to satisfy the following rule. So if you look at the S product of a sequence of operators, it up to signs, if you have fermions, it has to be the same as for the same operators with the rules I explained. And the fact that, putting the annihilation operators to the right, and there's this idea that inside S products, everything commutes. And he has a similar axiomatics for time-ordered products. But there you require that instead of ordering operators according to the fact they are creation or annihilation operators, you just put them in decreasing time order. So these are intuitively the two basic ways of, well, there are three ways of handling products actually. One is to do this Wick renormalization because you get rid of infinities. This one is consistent with the idea of causality. You want to apply operators in the order where in time orders, in time compatibility to the fact that, yes, you want to apply something that happens later after something that happened earlier. And then the last product is the operator product. And the three are connected. The operator product is slightly different than these two because these two products, S products and T products, are commutative. So we're going to see they can be related very easily by means of algebra techniques. Operator products that can also be related to them, but it's slightly, not much more, but slightly more complex because you're moving from a commutative product to an associative product. So you're really changing the essence of the product law. I don't think it discussed this. I think this is probably Lorentzian, but it doesn't matter because it just handles the fact that it's purely axiomatic. It just handles the fact that you have creation and annihilation operators that satisfy commutation rules. So if yes, 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 yeah. Yeah, yes. This is what I just said. Probably I said it wrongly, but the basic product in a certain sense is the operator product because you have creation and annihilation operators, which are operators. So they act on a space, whatever is the space, and they act by operator composition. But then starting from this product, you can also define these two other products and yes, exactly. Yes, yes. No, what I'm saying is perfectly consistent with what you said, of course, yes. Okay, so I'm using Wick notation. If you're curious to read this paper, I think you should, because it's very nice and very fundamental paper. So I will use his notation, although it's not perfect from the point of view of algebra, but his notation is the following. If you want to move from the time-ordered product of two operators u and v to the normal order or Wick product, because you have these commutation rules satisfied by creation and annihilation operators, the difference between the two is always going to be a complex number. I mean, in all the calculations I will do, because of the bracket rules relating creation and annihilation operators, every time you compute this kind of quantities, where u and v are creation or annihilation operators, what you get, the difference between the two products at this basic level, is always a complex number. And Wick has this notation. He calls this a contractions, which means that you're going to join u and v and compute the corresponding complex number. So in his paper, there are two main theorems, and I will explain them later. So in his notation, the first theorem says that if you compute the time-ordered product of a product of operator, then it's the same as the normal order product plus corrections that are obtained from these contractions. So in his notation, and so what his notation means is that you start from the normal order product of the operators, and then you're going to create all possible pairings or contractions between two operators in the expansion, and then you're going to create all, oh, sorry, I missed the term where there are only order one and order, oh, so contractions indexed by one dot and two dots. So here there will be a term where there are all possible pairings of elements in the sequence. Here, the notation he used is there to denote all possible pairings between of order 3, where you join randomly chosen element in the sequence with another one, then you do the same thing with two other components and with Wick components and so on. And so his first theorem is this statement, that you can go from time-ordered products to normal ordered products using all pairwise contractions. The second theorem is not stated as clearly, but this theorem 2 is about rules to compute these quantities. This is really a computation you have to do when you're doing field theory and you want to compute transition probabilities or scattering numbers. So the question is, how do you compute something like this, for example, where you have products, time-ordered products of operators, when it's in the expansion you include normal products. So what is the rule to achieve such a computation? And so he has a rule that he describes. I won't state it because I will explain how to make sense of this problem later in a systematic way. And he also mentions that there are similar methods that have been developed by Ourier and Kind, relating the operator product with the normal product. I will discuss them a bit at the end of the lecture if I have time. So, as I mentioned at the beginning, the point of the lectures is to understand how we can bring Hopf algebras in this picture. For those who are familiar with Hopf algebra, it's very natural because the foundation of all these computations is based on the idea of extracting elements in sequences and coupling them, these sort of constructions. And this is really what Hopf algebras have been introduced for, at least in combinatorics. So, as I said, probably there will be several lectures discussing Hopf algebras. I will give you the definitions, the formal definitions. So, a Hopf algebra H is by definition an associative algebra with unit. So there's an associative product and a unit, I will write eta. In this framework, it's natural to view the unit as a map from K to H. Instead, also an algebra map from the ground field to H, instead as an element, a particular element in H. Then it's also a co-associative coalgebra. With co-unit. The co-unit I will write epsilon. So co-associative coalgebra, for those who don't know what it means, you just obtain the notion by dualizing the definition of an algebra. So an algebra is classically obtained by looking at a map from the tensor product of A to itself to A. In a coalgebra, you dualize this process. And dualizing also the associative axiom, what you get is that this diagram is commutative. And then the co-unit is a map from A to the ground field, which has the dual property of a unit. So we can write this. So the co-unit axiom says that if you map H to H tensor H by the coproduct, so delta is called the coproduct, and you apply the identity tensor epsilon, or epsilon tensor the identity. So you map to the scalars, which means that you map H tensor H to H, and you want this map to be the identity. So this is really the dual axioms of associative algebra. And to have a Hopf algebra, you need that these two structures interact. So you want M to be a morphism of algebra. Of coalgebras, I'm sorry. Or delta to be, this is equivalent, delta to be a morphism of algebras. So here from tensor A to A. So I'm skipping some details, but that's the basic idea. And because the tensor product of two algebras is an algebra, And if you dualize the tensor product of two coalgebras is a coalgebra, and this is usually expressed by drawing a commutative diagram, saying that if you go from a tensor A to A by the product, and then you apply the coproduct, it's the same than going from A to A tensor A to the 4 by applying delta tensor delta. Here you apply the switch, permuting two elements. And here you apply M tensor M. Okay, so these three definitions are strictly equivalent, and there are some axioms saying that the unit and co-unit maps have some natural compatibility property that, from the diagrammatic point of view, are expressed by the fact that M is a morphism of co-unital coalgebras and delta is a morphism of unital algebras, in the sense that the unit and co-unit are preserved by product and delta. So anyway, okay, so when you have Hopf algebra, it's very interesting usually to move to its endomorphisms. And the point is that the set of linear endomorphisms of H is also an algebra. Which has a unit, which is the composition, I will write it eta, so the composition of the unit. No, sorry. Wait, new, and it's going to be the composition of the unit and the co-unit. So it's essentially the projection onto the ground field inside H. And the composition or the product law, so the convolution, because in many cases it agrees with standard convolutions, is defined by mapping H to H tensor H by the coproduct. Then you apply F tensor G, you go to H tensor H, and then you go to H by the product. So it's very easy to show that this product is associative. You have the similar structure on linear forms on H. In that case, the unit, so an algebra with unit, the co-unit of the Hopf algebra, and the law is given by the same rule. So if you have two linear forms, lambda and beta, you do the same construction, but then when you apply lambda tensor beta, you go to the ground field directly. And there's also an action on, so on linear forms, on linear endomorphisms in the following way. So I will write using always the same notation, the convolution product. So if you have a linear form lambda and a linear endomorphism of H, you can apply always the same construction. But then when you apply lambda tensor beta here, tensor F, sorry, you go directly to H. So we will set or use the following notation. So if lambda is a linear form on H, I will write phi index lambda for the convolution product of lambda with the identity map. And so this construction has several properties that I won't prove, but are very easy to prove. So first, if we introduce G of H as a set of linear forms which are unital, then this forms a group for the convolution product, provided some conditions, some technical conditions are satisfied. These constructions, these conditions are always satisfied in the case I'm going to consider. So for example, they are satisfied if H is a graded Hopf algebra and connected. So which means that H decomposes as a direct sum, which H0 equal to the ground field, and the product goes from Hn tensor Hm to Hn plus m, and the coproduct goes from Hn to the direct sum of the tensor product Hi tensor Hi with A plus J equals m. So provided these kind of conditions are satisfied, G of H is a group. And so the inverse of an element is obtained by from this identity that you expand as a formal power series that has only a finite number of terms in this kind of situation when H is graded. And some other properties are also straightforward from the definition. For example, if you compose phi lambda with phi beta. So this anamorphism of H induced by linear forms. You can compute. What you get is that this is phi lambda beta convolution with the identity. This is beta convolution lambda convolution the identity. This is I beta convolution with lambda, which is equal to phi lambda convolution with beta if the coproduct is commutative, is co-commutative. So here I should probably introduce some notation. Due to Swidler, which says that it's common to write delta of H as H1 tensor H2, H tensor H. It's really a shortcut because it's not true in general that you can decompose an element in the tensor product of two vector spaces in that way. In general, you cannot, yes, you cannot have this form. You have to have a linear combinations of terms of this form when you're creating tensor product. So this notation is a shortcut, but you have to recall or to remind that it's a shortcut notation, that the precise form of the tensor product is not this one. It's the linear combinations of terms. But anyway, this notation is very useful because it's very synthetic and you can use it without trouble if you basically stick to some reasonable rules that are not expressed, but I mean, everyone dealing with Hopf algebra knows when he has the right to use this notation, which is essentially all natural computations on Hopf algebra can be handled with this notation. It's usual when you iterate the coproduct as a map from H to H tensor n, to write this as H1 tensor H2 tensor Hn. So the coproduct is co-associative, which means that when you want to iterate it, you have to choose the place where you're going to apply it on tensor products. For example, you would have to decide the way you go from H tensor n minus 1 to H tensor n applying the coproduct, but because it's co-associative, it doesn't matter where you let it act. So this notation makes sense. Because there's no ambiguity on the way the iteration of the coproduct is defined. And then I will use these notations to make some computations. There is some ambiguity when you look at this because here the H1 and the H2 are not the same as at this level. So this notation seems to be inconsistent, but it's not in practice. Once again, there are some set of rules when dealing with Hopf algebras, and you have to be careful when you interpret the meaning of the symbols. But so just be careful that the H1 and H2 here are not the same as here. And so, for example, I will look at an example. What happens if I look at the co-associativity property? So if I compute this is the same as delta tensor id applied to H1 tensor H2. And this is going to be H1 tensor H2 tensor H3. So you see here the kind of things you have to be aware of. If I was purely consistent, I should say that this is equal to H1 1 tensor H1 2 tensor H2. But then I reorganize the notation in such a way to end up with this notation. So if you have the feeling later I'm doing inconsistent computations, they are not inconsistent. I'm just using implicitly this kind of rules that make sense if you're a bit careful. So co-associativity, just to conclude, means that, co-commutativity means that H1 tensor H2 is equal to H2 tensor H1. In abstract terms, delta is equal to the switch operator composed with delta. So now I can use the properties I explained about convolution product to make the following observation. So since GH is a group, I can invert for the composition product. So this is the inverse for the convolution product of phi lambda. And what I get is this is phi, the inverse of lambda for the convolution product. So there's a consistency between what happens in the algebra of linear forms and when I induce from these linear forms operations on the Hopf algebra. So the main claim is that this construction is enough to understand many Wick products. The reason is the following. So given lambda in G of H, a unital linear form, so phi lambda is a vector space endomorphism, but also a linear isomorphism. And therefore, we can define new product and new coproducts in the following way. We write them dot lambda, delta lambda, and there's also a new co-unit that I will write epsilon lambda by the following equation. So we simply conjugate the initial product using the isomorphism. This is usual structure transportation. So anytime we have a unital linear endomorphism of H, we can perform this, this computation. And because this is structural transportation, when you transport an algebraic structure by linear endomorphisms, you get a new isomorphic structure. We get for free that H equipped with this new product and the new coproduct plus the initial unit map. This is because lambda is unital, that we can use this for the algebra, the new algebra, we can use the same unit map. But we have to change the co-unit. So this family is of algebra. And the map I lambda composition inverse is an isomorphism between the initial of algebra and the new one. And then there are some observations that can be done. For example, if phi lambda is say algebra morphism, then the new product you obtain will be the same than the initial one, because in that case, this relation is just a relation telling you that phi lambda is an algebra morphism. If phi lambda is a morphism of coalgebra, then the coproduct is going to remain the same, and so on. So there are some obvious observations that you can and results that you can get out of it. Much time do you have? 5? 4? Okay, then I will explain you several applications of this construction. So I will explain how we can recover the Wick calculus of Wick. I will explain how the construction can be used in probability. But I will start with something slightly different to show that Wick calculus is, I mean, can be used beyond the framework I've started to describe. And I will, as a first application, explain how it applies to what is called the multiplicative renormalization. I will just sketch the explanation. If you want details, you can read the articles I mentioned at the beginning. These two articles on what we called with Kurush exponential renormalization. So this is a direct consequence of what we did. The idea is the following. In classical QFT, so there's a notion of Feynman diagrams. So for example, if I have this diagram, and so these diagrams are supposed to describe physical processes, for example, a particle entering and exiting the system and undergoing some transformations, some interactions between so the initial time and the final time. So we have this type of diagrams describing physical processes, and there's a way to assign to each of these diagrams what is called an amplitude. Which is ideally a complex number, but in practice, infinities pop up, and you have to handle the fact that you have to renormalize this quantity. So there are many ways to do it, but often this is done by regularizing in a certain way the amplitude in such a way that it goes to an algebra of this form. And what people do in this situation to remove the infinities, the modern explanation is to use Kohn-Kreimer renormalization that I will mention maybe later. But earlier, people were doing this by hand at the very beginnings of renormalization. And now would they perform renormalization? They will perform it inductively on subdiagrams. So more precisely by induction on degree. Diagrams have a degree. Which is the number of edges minus the number of vertices plus 1. And so renormalization is performed by induction on degree, starting from the ones of lower degree. So for example, if you assume that there's a problem with this very elementary graph, so that computing its amplitude is going to give you a decomposition of this form. So if you're in a situation where you have trouble with this ill-defined term, because when you let this, say, so-called perturbation parameter go to 0, which is what you want to do, you end up with infinities that you want to get rid of. So there's a simpler way to perform renormalization on this simple graph, which is to remove this term. So in this graph itself, so in the computation of the amplitude of this graph itself, but also in all higher order graphs. And if you look at textbooks, I think this is done that way in on Zuber and maybe in the book of Collins. In many books on renormalization from the 70s, or you find a way to express this, a graphical way to express this process. So when you have a graph like this, and you have divergences appearing in relation to a subgraph, maybe something like this, you will associate to the graph a new graph marked by a cross. And this cross means that you're going to compute the amplitude of this graph in the usual way, but you have to remember to remove phi minus of the subgraph in the computation. So in a certain sense, you mark the graph by minus phi minus of this. So and you do this by looking at all subgraphs of graphs. This is called, I think, multiplicative renormalization. And you can do this whatever the process you choose to perform renormalization. I mean, there are plenty of ways of doing renormalization, and all fit this construction, because this is a basic recursive construction that does not involve much in algebraic terms. So now we know that, or many of you know that there is a Hopf algebra structure on graphs. Which was introduced by Kramer, and he developed it with Kohn, which is obtained by, if you look at a graph, the coproduct is going to map the graph to the sum over all subgraphs of, say, gamma tensor gamma over gamma. I don't explain the meaning. I don't want to spend too much time on this, but the idea is that you have a notion of subgraph, and you extract this subgraph, you put it to the left, and you contract the initial graph by contracting all the subgraphs to a point. For example, if I take the same example, or this one, if I choose gamma as a subgraph, I would go to this tensor, and so on. But I could remove several subgraphs. I could also remove another graph. I will put it here in this left-hand side part. And as an algebra, the Hopf algebra is simply the free commutative algebra over all graphs of the theory. Now, how can I encode Hopf algebraically multiplicative renormalization? I can use, yeah. Yes, okay, just very briefly. I can use this quantity to define a linear map from H to C that maps this elementary graph to minus phi minus the graph, and all other graphs to 0. Then I can take the exponential, the convolution exponential of this map. We call this gamma indexed by the graph. And the point is that I just state this as a claim. Multiplicative renormalization is equivalent to sending H to itself by applying what I define as phi indexed by a linear form that in that case is gamma of the graph. So this is the first example where you can use Wick calculus, because I will show you during the next lecture that classical Wick calculus is really encoded by the same process. This is the first example, different situations than the one I mentioned, where you see that this process is very universal and is able to explain several constructions, not just the ones initially devised by Wick and others, but also more advanced constructions, like the one, like the Hopf algebraic approach to renormalization. And just to conclude, a few words. What is nice with this construction is that really it depends essentially on nothing. It just depends on the idea of recursion of the degree of graphs. You're going to apply this construction iteratively, taking higher and higher graphs. And this will allow you to normalize the theory at any order in perturbation theory recursively, which is what people did with multiplicative renormalization. But you essentially assume nothing on the way you extract divergences. So you can extract divergences in the way I explained here. It's called so using essentially dimensional regularization and minimal subtraction. Minimal subtractions mean that you're extracting the divergent part in Lorentz series in the obvious way. But you could apply the constructions to arbitrary schemes of extractions of divergences, even more involved one. And this is what we call exponential renormalization, because the exponential comes from these terms. The fact that you encode multiplicative renormalization recursively by using this exponential trick.
Sorry, maybe I missed it, but when you defined the Hopf algebra, where is the antipode?
Oh, I forgot the antipode. Yes, you're right. Yes, I forgot the antipode for a simple reason. In the kind of situation I'm considering, there's always an antipode because I'm always in a situation where this hypothesis apply. So I mentioned that if I want to make sense of the fact that the set of unital linear forms is a group for the convolution product, I have to make some technical assumptions. These technical assumptions, they imply automatically also the existence of the antipode. And so, so I'm sorry for omitting it, but you're right, of course. In general, well, I should say this because people are going to use Hopf algebras again, and maybe they would need the antipode. So, And the axiom of the antipode says that the identity as an inverse for the convolution product usually it's written S, and so it's defined by this property. Okay, I'm sorry that you thanks for pointing this out, because I'm so used to working with connected quantitative algebras that I very often forget to mention that there's an antipode, because it's a consequence of the structure you have in this setting. It's also I mean, in many situations, even if it's not connected quantity, there is automatically an antipode. So.
Okay, thanks very much. Thank Frederic again.